So now that we've talked about the normal distribution and what it means to be a z-score, now we want to look at being even more precise than we were with the empirical rule. With the empirical rule, we said there's about 68% of the population within one standard deviation of the mean, and about 95% of the population is within two standard deviations. Well, those are some rough values, and of course we have the 99.7 for within three standard deviations. But what we want to look at now is how to be more precise to say, what if I want to know what percentage of the population is going to be 2.17 standard deviations above the mean or less? Or maybe how many are going to be a half a standard deviation above the mean or more? And so that's what we want to look at now. Now, we have the chart, the table. So keep in mind you have this table here that you got from the module. This gives you the probability of being less than a given z-score. Now, just to remind you, the way that we're going to use this is we're going to find the z-score that if we wanted negative 1.97, we'd come to negative 1.9 and see where it meets over at the 0.07, and then this would give us the probability of being less than that value. So if we come back to the problem that we're looking at, we're being told to assume that the readings at freezing on a batch of thermometers are normally distributed with a mean of 0 degrees and a standard deviation of 1 degree Celsius. A single thermometer is randomly selected and tested. Find the probability of obtaining a reading less than negative 2.259 degrees Celsius. Now, this particular case, the values given to us are going to be z-scores because of the fact that our mean is 0 and our standard deviation is 1, which is what we call the standard normal distribution. But if we look at how far away our data point of negative 2.259 is, well, that's negative 2.259 standard deviations away, since the standard deviation is 1 degree. So we're looking for, on the standard normal distribution, we're looking at a z-score of negative 2.259, and we want to know the probability of being that value or less. This basically tells us that we could look at the chart, find this value, negative 2.259, and that's going to be the answer, because that chart gives us the probability of this z-score or less. So to find this value of negative 2.259, that's about negative 2.26, since our table only goes out to 2 decimal places. So we're going to come down to the negative 2.2 area and say it's going to be somewhere along here. And then we're going to come back up to the 0.06 and come down and see where those meet at. And we can see that they meet here at 0.01191. And so this is the percentage or probability of getting that negative 2.26 or less. Now, what if the value that you're looking at isn't on the standard normal distribution? So here's an example of that. So here in this country, the United States of Heightlandia, the height measurements of 10-year-old children are approximately normally distributed with a mean of 56.9 inches and a standard deviation of 8.6 inches. And we want to know what's the probability that a randomly chosen child has a height of less than 59.2 inches. And so what we need to do in order to figure that out is we need to look at the z-score. And so that's the big thing, that if you're not given the z-score, you got to calculate it. So remember, calculating a z-score means let's take our data point, our x, let's subtract the mean from that, and let's divide by the standard deviation. So in this case, the x value is 59.2, our mean is 56.9, and then our standard deviation is 8.6. And so if we put this into our calculator, I'm going to do this off screen, but you can follow along by typing into your own calculator. This z-score is about 0.27. So we're going to use this and we're going to go look at our chart and see where a z-score of 0.27 would be. So if we're trying to find a z-value of 0.27, then on our chart, we're going to look at the 0.2s, then we're going to find the 0.07s and see where they meet at. And so it's looking to me like the probability of z being less than or equal to 0.27 is going to be about 60642. So we can pop back over here and say 60, I think it was 6062, right? 60642. And so this is our probability of being less than 59.2 inches. Now let's get a little bit trickier. Let's look at the probability of being greater than a certain score. So what we're going to do here is think about what's going on with our picture of the normal distribution. And to say, if my goal is to calculate, and I'm not even looking at this problem yet, so I don't know if it's even a positive z-score or not, but our goal when we're looking for greater than is going to be to calculate that probability or that area on the normal distribution. Well, the problem with that is that the table that we have gives us what I have here in green. So what we have to realize is that the whole curve is 1. It's a probability of 1 that you're going to be underneath there. So if we subtract off the green, so if we subtract the green from 1, that should equal the yellow that remains. And that's our basic idea because 1 would be the whole thing. So if we subtract off the green, it leaves us with just the yellow. So if our goal is to find the yellow, then we can use the table to find the green, and then do 1 minus that value in order to figure out the probability of being greater than something. So let's look at this problem now. We want to assume that the readings at freezing on a batch of thermometers are normally distributed, so same idea as that first one. A single thermometer is randomly selected and tested. Find the probability of obtaining a reading greater than 2.278. So now that we've read it, let's look at what's going on. We got this value of 2.278. We know the closest we're going to get with our chart is 2.28. So if we want to look at the probability of being greater than that, then our goal of this problem is to find this value here. So if we bring up our chart, we can try to find the z-value of 2.28 on our chart. So I'm looking at just the relevant portion of the chart right now, where we know we've got our 2.2. And then if we come down from the 0.8 portion, we can see this is 0.9887. So in that non-shaded area of the curve is the 0.9887, because remember the table always finds the probability of being less than a certain z-score. So if I want to figure out just the yellow portion that I've shaded, which is the goal of this problem, then that's going to be 1 minus the 0.9887. So if you grab your calculator and do 1 minus 0.9887, then you're going to find that that probability is about 0.0113. And that's what we're looking at. Now let's talk about finding the probability between two given scores. So let's make sure we understand the basic idea on how to do this first, and then we'll go through the actual nuts and bolts of it. The basic idea of what's going on a problem like this is if we look at the normal distribution chart. Oops, let me draw a little straighter line there. And we've got this z-score. This one is the negative 0.77 that's given to us. And we've got this other one that's negative 2.1. Now, if we think about the table and what we can do, we can use the table to find this probability over here. That's good. We could also use the table to find this probability over here. But what we're looking for in this problem is what I have in yellow. So the goal of this problem is to find the probability of being between these two values. So if we think about this geometrically, then the way we can do that is to take the bigger value. So we can take this big green one, and if we take that and subtract off the purple one, so what that's doing there is that's lopping off this portion of it. And that would get us back to what we're trying to find. So we're going to say the good part. Yay! So if we can take the green and subtract off the purple, that's going to get us the yellow, which looks something like this. So geometrically, that's what's happening. So we're taking the green guy, lopping off his left side, subtracting it off. So in terms of our table, we're going to say if I could find the probability that my z is less than the negative 0.77 and subtract off the probability that the z is less than negative 2.1, that's going to get me my good value that I want. So now let's go ahead and go to our table and let's find those values. So for the negative 0.77, we're going to find the negative 0.7 and 0.07. And we can see that they meet at 0.22065. So 0.22605. And then we're going to look at the purple here, the negative 2.1. That's pretty easy. That meets right here. That's 0.01786. So 0.01876. Let's make sure I jot down those numbers right. 0.01786. 786. There we go. And now if I subtract those two values, I'm going to do that with the calculator. And again, this is not a fancy calculation, so we'll just go ahead and do this off screen. This value is 0.20819. And this gets us the probability of being between those two values by taking the larger one and subtracting the other. Now, of course, some common mistakes here is doing the subtraction in the wrong order. So if you get a negative number, you probably made a mistake. If you end up somehow with a number bigger than 1, you made a mistake somewhere else. So think and make sure your answer makes sense when you look at it. Now, if you're looking at values that are given as x values instead of z-scores, then obviously your first step is going to be convert them to z-scores. So in this case, we've got this particular fruit's weights are normally distributed. There's a mean of 263, standard deviation of 12, and we're measuring in grams here. If you pick one fruit at random, what's the probability it's going to weigh between 233 grams and 257 grams? So the goal of this problem is to find the probability of being between 233, wow, I can't write the right numbers there, 233 and 257. So we're going to try to turn those into z-scores. So 233 as a z-score, we're going to subtract the mean of 263 and divide by 12. We can see that it's less than the mean, so we get a negative number here. So as we do this division, we're going to get negative 2.5. That's pretty far below the mean. Now this other z-score here of 257, we can see he's also going to be negative. He's also smaller than the mean. So we're going to do 257 minus the 263 and then divide that by the 12, the standard deviation. He's only at negative 1/2. So we're looking for the probability of a z-score to be between negative 2.5 and negative 1/2. And then again, if we want to use the table here, oops, this should be z, not x, sorry. So if we want to use the table, what we're going to do is we're going to find the probability that a z-score is less than negative 1/2, and we're going to subtract that from the probability that a z-score will be less than negative 2.5. And so now it's a matter of using the table to find those two values. Now at this point we should have some practice using the table, so I'm going to go ahead and just jot down the values that we should get from the table. Did you see how fast I wrote those down? The magic of media. So once you look at the table, those are your two values. And if you want to find the probability of being between those two values, then we'll go ahead and subtract them. I'm doing that off screen right now. And it looks like we're going to get about 0.30233. So in summary, we basically looked at three different things. We found the probability of being less than something. We're just going to approach the table. Now, if that something is a z-score, we can just look straight at the table. If it's an x value, if you're given a value where the mean isn't 0 and the standard deviation isn't 1, then you got to find the z-score first. Now, if you have the probability of being greater than something, we're going to do 1 minus the value from the table. And if we're trying to find the probability of being between two values, then we're going to do the table value from the bigger one minus the table value from the smaller one. Now the last topic for this video is going to be margin of error. And I'm not going to spend a ton of time on margin of error because margin of error is actually a super complicated thing that you can study in a statistics class. We're going to get the basic idea of it here and how to calculate one variation, a very simple way to calculate a margin of error. Now we can get a much more precise version if you take a statistics class. We can discuss it in much more depth. But here's the basic idea. So we said at the very beginning of this whole unit that one of the main ideas of statistics as a whole area of study is to be able to try to make inferences about a population by just taking a sample and looking at that sample. What the margin of error is doing is the margin of error is a way of saying when I take my sample, it's probably not going to be perfect for the population. I might be off by a little bit. So if let's say we're taking a sample during a presidential election year and we're trying to look at candidate A and candidate B, and we find out that 48% of people are in favor of candidate A. Well, we found this out from taking a sample of, say, 1,000 people. Well, maybe our sample wasn't perfect. Maybe that's not going to exactly match everybody in the U.S. and how they vote. We might be off by 1% or 2%. And that's what the margin of error is the margin of error is going to show you what the maximum likely difference is between our sample value that we found from sampling the population and what the full population actually feels like. So it doesn't have anything to do with an error in calculation or anything like that. It has to do with an error in how we sampled the population. To say, we did our best, we did a simple random sample, but you know what? It just might not have matched up exactly. Now, like I said, there's very precise ways you can do this once you learn more statistics. We're going to use a decent estimation. Our decent estimation for the margin of error is going to be 1 over the square root of n, where n is your sample size. Now this is going to give you a value as a decimal, and so if we want to turn that into a percent, we're going to multiply that by 100, and that's what was mentioned in the learning module. So as far as the actual calculation, it should be very simple, that we're just going to say, in this case, our sample size was 368, so it's 1 over the square root of 368. So if we just grab out our calculators and I do a fraction of 1 over, square root is second and then this x squared, and then we do 368. So yeah, we get this value. Yeah. Turn this into a decimal. So hit that button above, enter, and we get this decimal value. And if we wanted to turn this into a percent, we could then multiply that by 100 to find out it's about 5.21%. So we can see with this sample size here, this isn't the best. That if this were, say, a presidential election year and we were trying to look at 48% of the people were in favor of this one particular candidate, we might be off by 5%. So this person that might end up, that we might think currently is in the minority, they might be as high as 53%. So even though in our sample that we looked at, only 48% of the people were in favor, the actual population might be 53%. And that's why sometimes you'll hear commentators talking about, oh, this race is within the margin of error. And that's what they mean, that if candidate A is at 48% and candidate B is at 49%, then that 49% might not actually be winning. Because maybe they're actually 2 or 3% lower than that, and maybe the other person is 2 or 3% above that. And so that's what we mean by within the margin of error, is that if the scores are within the margin of error of each other, we actually don't know who's winning. But if one candidate's at 40% and the other's at 50%, and our margin of error is 5%, then we're like, okay, wait a second. Yeah, in that case, we can be more confident that this person is in the lead. Let's now look at a problem in which we're given the percentile and we're being asked to find the data point that goes along with it. So we're told to assume the readings at freezing on a batch of thermometers are normally distributed with a mean of 0 degrees and a standard deviation of 1. Now this is really important, the fact that we're told that the mean is 0 and the standard deviation is 1, because this tells us that we're looking at the standard normal, which means that our data points, our x's, are the same as our z-scores. So we really just need to find the z-score with the given condition. And the given condition is that a single thermometer is randomly selected, and we want to find percentile 13, so the 13th percentile. This is the temperature reading that separates the bottom 13% from the top 87%. And so if we think about the normal distribution, what this is asking us for is it's saying, at what z-score will we have 13% below us and 87% above us? What's that threshold going to be? As far as our table then, we're going to be looking for having 13% less than us, or 0.13000 in the table. So we're going to look at our table and try to find the value closest to 0.13000. And so as we look in here, there's two values that jump out at us. There's this value of 0.13136, and that's associated with z equals negative 1.12. And there's this other value of 0.12924, and that's associated with z equals negative 1.13. We know that 0.13 is somewhere between them, and so let's see which one is closer. The first one is 0.00136 away. This one is 0.00076 away. So it looks like this guy over here is closer to our 13% that we were looking for. And so to answer the question, a z value of negative 1.13 would separate the lowest 13% from the highest 87%. And because, going back to our problem, our data points were normally distributed using the standard normal, this would also be our temperature reading of negative 1.13 degrees Celsius. And that's the final answer to the problem then. Now, if the problem told us a different mean and a different standard deviation, then we could use this z-score to find that data point. But basically with these problems, we're working from the inside of the table out. We're finding the percentage to the left inside the table, determining the z-score on the table from that percentage, and then we can find the data point from that z-score.